Alright guys, we're back with another lecture here. This one's on 6.3. It's sort of a continuation from 6.1 where we talked about linear transformations, what they are, definitions of linear transformations. And I mentioned a couple words in those in that first lecture on linear transformations that I wanted to explore a little bit more in this particular section, namely kernel and range. Okay. So again, suppose we have a linear transformation here. We'll call it T, and suppose that T maps U into V, where U and V are vector spaces. Okay, then we can represent these things, and we tend to represent arbitrary vector spaces as like blobs, right? So let's say this is space U. I don't know what it is. Okay. And maybe this is space V. Okay? All right. Now, what I know just by virtue of the fact that U and V are vector spaces is that they both have a zero vector. So I'm going to go ahead and put that in here because that's going to be important. Okay? So there's the zero vector of U. Okay? And we'll say that the zero vector of V, I don't know, it's right here, I guess. Okay? And again, these are not necessarily the same element, right? So again, the zero vector for the real numbers is the number 0, but the zero vector for, let's say, M2 is, of course, the 2 by 2 matrix where all the entries are 0. That's not the number 0, okay? But they each have their own zero vector. Now, what I know is that because T is a linear transformation, I do know that T will map 0 to 0, right? Because of the properties of scalar invariance and the properties of additivity, I know that T of the zero vector for U is definitely going to equal the zero vector of V. Okay, so I know that to be true. However, maybe something else might get mapped to 0 as well, right? Maybe it's possible that not just one element gets sent to 0, but multiple elements get sent to 0. For example, let's say I define T, I'll put this in another color because it's not a general definition. Let's say I'm defining T, which maps M to R, and it maps it to the real numbers. And I say that T of some matrix A is just whatever the A11 value is. Okay? Well, this is a linear transformation. It's additive, it's scalar invariant. Now what we notice, of course, is that the zero vector here, okay, of course gets mapped to 0 because the 1, 1 entry is 0, it gets mapped to 0. But honestly, anything of this form gets mapped to 0, right? So this matrix would also get mapped to 0, right? And this matrix would also get mapped to 0, right? In fact, the only matrices that don't get mapped to 0 are the ones that don't have a 0 in their 1, 1 entry. And so it's possible that inside of U, inside of my domain here, maybe I've got a whole group of things, okay? And all of these things in here, right? All of these things, they all get mapped to 0, right? All of them, right? Okay. This space, right? This space where all of the objects that get mapped to 0 in the codomain live, this space is called the kernel. Okay, so that's the kernel of T. And I'm going to give you a formal definition for the kernel in a second. Okay, a set theoretic definition. Okay, all right, fine. Okay, so U is my domain, V is my codomain. the range, well, the range is all the things that I could hit, right? So again, let me give you another example here. Suppose T, and we're going to map R2 into R4, where T of x comma y is given by x comma y comma x minus y comma 0. Okay, this is a linear transformation, but and 0 gets mapped to 0, but I can't hit every vector in R4, can I? Right? I'm just, things in R4 have 4 components. So as an example, is there a vector which when I apply T, let's say will give me the vector 1, 1, 1, 1? Well, no, right? I already know that everything T maps into has a fourth coordinate of 0. This has a fourth coordinate of 1. It's not going to be in there, right? So in my map here, what I'm looking at is a situation wherein inside my codomain, I've got these places where domain values might get sent, right? So maybe this element goes here, and maybe this element goes in here. But it's also possible that outside of this, I may also have some values that nothing gets mapped to, right? Okay, well, this collection here, this space here where everything gets mapped, this is what's called my range. Okay, there's easy examples of this from something like college algebra, right? The range of f of x equals x squared is 0 to infinity, right? The negative numbers are not in the range, okay? The codomain of that function is all real numbers, because when you put something into that function, you're going to get out a real number, right? So the codomain is all real numbers, but the range, it's not all of them, right? It's just 0 to infinity. Same principle here, right? Only the spaces we're going to be looking at are going to be more dimensions than just R. Okay? So let me give you a formal definition for these things, and then I want to divide. We're going to look at kernels and ranges for some examples of linear transformations, but I want to look at I want to split them into 2 categories, because on one hand, for one particular type of linear transformation that we look at, this is going to be very easy, right? Finding the range and the kernel are going to be very, very easy. So first definition here, we've got the kernel of T, okay? And again, this is all the vectors in U such that T of U is equal to the 0 vector, okay, in V. Okay, yeah, and again, that's just what we said, right? So this is all of the stuff in my domain that gets mapped to 0. Okay, range, again, we can write it. Now the definition I'm going to give here, I don't like the one in your book. It's just not very descriptive. So this is going to be a little bit more wordy. But I'll use some English to make sure we don't get overloaded with some symbols here. Okay, so my range, that lives in my codomain. Okay, so my range, that's all the vectors in V, in my codomain, such that there is at least one U where T of U equals V. Okay, so if you've got at least one thing in your domain that gets mapped to you, you're in the range, right? And that makes sense. Okay. Again, it's possible we use these things, these formal definitions. It's better to have a good idea of what they mean. Okay. So I want to talk about some very, very specific examples. We've been talking about linear algebra for a while, and we made somewhat of a big deal in the last couple lectures about redefining matrices not necessarily as vector elements or elements of vector spaces, but as maps between real number spaces. Okay, things like taking a 2x3 matrix and using that as a map from R3 to R2, right? We call these maps linear transformations, which are defined by matrix multiplication. Okay, so suppose that I have a linear transformation T, which maps Rn to Rm, and so we define the action of T on some vector that I pulled out of Rn to be equal to A times V for some matrix A, which is an M by N matrix. Okay. Again, maybe a concrete example here. I've got let's map T is going to map R4 to R2, and we define T of V to be the product of, let's say, 2, -6 to 8, and -1, 3, -1, -4 times V, right? So take out some vector from R4, multiply it times this matrix, you'll get a two-dimensional vector, a two-component vector rather. That's something in R2, right? So we can define a linear transformation this way. Okay? And in the case where we define a linear transformation with this matrix multiplication, the kernel and range are actually really easy if we think about the definitions, right? So the kernel are all the vectors that you would put into this and get 0. But if I look at the definition, that's all the vectors that you multiply this matrix by to get 0. But we already have something with that definition. Okay? That's the null space of this matrix. The null space of A, that's all the vectors that you multiply A by in order to get 0. So for these types of linear transformations, they're the same. Right? In this particular case, the kernel of T is equal to the null space of A. And we know how to find null spaces from our previous, some of our previous examples. I'm going to work this one out in a bit. Okay? Well, what about the range? What about the range? So the range may be a little bit harder to think about. Okay? But the range is going to be the column space. Why the column space? So when I multiply this times a four-dimensional vector, okay, what I get is I get row times column, right? Yeah. But in reality, whenever I multiply those things, I'm not getting a whole lot of variation, right? I'm getting actually the sum of each of these columns times those vectors, right? So whatever value, so I'm just going to write this. So A, B, C, and D, right? So in reality, what I'm getting is I'm getting 2 times A plus negative 6 times b plus 2 times c, etc. But notice that in the bottom row, only this one gets multiplied times a. It's negative 1 times a, 3 times b, etc. And so I can look at this instead as a times 2 comma negative 1, right? Because 2 negative 1s will get multiplied by a. Plus b times, so negative 6, that's what we multiplied times b, and 3 gets multiplied by b. Okay? Plus c times 2 negative 1, etc. And so what we see actually is the range, the things I could possibly get out of this, is a linear combination of all of my column vectors. Okay? Well, yeah, but isn't that just the space that can be spanned by your column vectors? And yeah, it is. Yeah. So what we have here is that our range also very easy. Okay? So my range of T in this case is my column space of A. Okay? We can do these very quickly. To find my null space and my column space, I'll just work this one out real quick. Of course, we put this into row echelon form, and I made this somewhat easy to put into row echelon form. Okay, so let's take 2, negative 6, 2, 8, negative 1, 3, negative 1, negative 4. The row echelon form here is 1, negative 3, 1, 4, 0, 0, 0. 0. The second row is a multiple of the first row, right? So I kind of made it easy. Okay. And so I see for my column space, and hence, of course, my range, I just have the one column, right? Go to your lead one, go back to the original one, okay? And I can already write down that the range, so from this we can write down that the range of T is the span of just that one vector. Okay. So the range of T is just that one vector. Okay. What about the null space? Well, again, for the null space, we just sort of assume a zero solution column here, and then we parameterize and come up with a basis the way we normally would for solving a linear system. So in this particular case, we can let x2 be R, x3 be S, and x4 be T. I need to parameterize 3 of these because I only have one rank here. And then that top equation just reads x1 minus 3x2 plus x3 plus 4x4 equals 0, which of course we can just rewrite as x1 equals 3 R minus S minus 4T, just by moving everything over to the right. Okay. This allows me to come up with 3 basis vectors. Again, just rotate which of these parameters gets to be 1, the rest of them get to be 0. Okay, so let R be 1, S and T be 0, R be 0, S be 1, T be 0, etc., etc. We've done this before. Okay. And very quickly, let me write down some basis vectors. If I let R be 1 and the other ones be 0, that's 3, 1, 0, 0. Swap it around. I get negative 1, 0, 1, 0. And if I let T rather be 1, that's negative 4, 0, 0, 1. So those are a set of basis vectors for the null space. I can go ahead and write these down. I'm going to write down my null space just because I want to draw your attention to one more thing before I move on and do maybe a more interesting example. Not null space, sorry. That is my null space, but that wasn't what I was trying to find. I was trying to find the kernel of this, right? Okay. So the kernel of T, that's the span of, again, that list of vectors, 3, 1, 0, 0, negative 1, 0, 1, 0, and negative 4, 0, 0, 1. Perfect. Okay, now when we did row spaces and column spaces and null spaces, we had this theorem from the rank nullity theorem, right? And what that said was, it said that n was equal to the rank of A plus the nullity of A, the nullity being the dimension of the null space. Okay? And we can draw a parallel of that theorem here, right? Clearly, the rank of the kernel and the rank of the null space, the dimension of the kernel and dimension of the null space, they have to be the same because they are the same, right? So the null space here has 3 basis vectors. It has dimension 3, and therefore the kernel obviously also has dimension 3. But what about the rank? Well, the rank is the number of non-zero rows in row echelon form. Yes? But if you tell me a matrix has 5 non-zero rows in row echelon form, then I can tell you that it has 5 leading ones, because every row that doesn't have all zeros in it has to have a leading one, right? But if it has 5 leading ones, then the basis for my column space, I'm going to take those 5 columns from my original matrix. Look here. This one has rank 1. It's got 1 non-zero row, so therefore it has 1 leading 1. And I only selected 1 column as a basis vector for my range, for my column space. But what that means is that the dimension of the range is the same as the dimension of the column space. Okay? And that's the same as the rank. Well, this leads me to a different rank nullity theorem that says for some linear transformation T, okay, all right, so for some linear transformation T, the dimension of the domain is equal to the dimension of the kernel plus the dimension of the range. This is the same, right? Now let me write the previous version we had was n. N is the number of columns, but notice that the number of columns, that has to be the same as the number of components in the vector I'm multiplying by, right? This is m by n. The vector has to be n by something. So I have an n-dimensional domain. Dimension of the kernel, this was the nullity. And the dimension of the range, this was the dimension of the column space, which we said was the same as the rank, right? Yeah. So again, these linear transformations based off matrix multiplication, these are very, very nice. They're very easy to work with. Again, we already know how to find things like column spaces and null spaces, and so we already know how to find things like kernels and ranges for these linear transformations. Now, what if we don't have those? Well, okay, we can do, let's take a look at maybe another example. Okay, maybe a slightly more interesting example. I'll just pull one out of your book. Again, some of the problems that I have assigned to you guys are going to have you look at a linear transformation and just consider what it means for that linear transformation, transformation's mapping. And it's going to ask you to talk about things like the kernel and the range. Now, full disclosure, just a little hint for you. It is almost always easier to find the kernel than it is the range. Okay? If you're asking me, what do I plug in that will make me get 0? I have a lot of techniques to find that, right? If you're asking me to list all the values that I could possibly get out of this, mapping, that's harder, right? So it's almost always easier to find the kernel than the range. But let's take a look at one. So let's see. Sorry, I want to check the ones I gave you guys for homework. Didn't want to do one of those. Okay, here we go. So we have, consider the linear transformation which maps, so T, it's mapping R2 to M23R. And the action is, so T of some vector xy gets mapped to the following 2 by 3 matrix. We have negative x minus y, 0, 2x plus 2y, and then 0, 3x plus 3y, and negative 9x minus 9y. Okay. Okay. So we're given that this is a linear transformation. Okay. The spaces are R2 to M23. And they want us to find both the kernel and the range. Now, real quickly, I do want to mention something. Okay. It's useful for us to sort of consider the size of the space for our domain and the size of the space for our range, because you cannot create more dimensions than you started with. So for example, in this case, R2 is 2-dimensional, right? The things in R2 have 2 components, 2-dimensional. M23 is 6-dimensional, right? There are 6 sort of free choices when you're making a 2 by 3 matrix, okay? So I'm taking a 2-dimensional space and mapping it into a 6-dimensional space. Then I can already tell you the range. The range can't be more than 2, right? Yeah? If I only start with 2 dimensions as my domain, I cannot take those 2 dimensions and, I don't know, sprinkle some magic dust on them and turn them into 4 dimensions. I can't, right? So I already know that whatever my range is, at most, dimension 2. Now, okay, fine. That means my range is not going to take up all of M23, right? It can't. That's 6-dimensional. My range is at most 2 dimensions. There's going to be a lot of stuff in M23 that I can't possibly hit, okay? So, okay, let's take a look at this. Let's do the kernel first. Okay, let's do the kernel first. So again, the kernel. So we remember again, the kernel, it's all the things that we can plug in here in order to get the 0 vector. Well, the 0 vector in M23 is just the matrix that has zeros at every component. Okay, fine. And this is supposedly equal to some mapping of a vector xy. Well, yeah, but if these 2 matrices are going to be equal, each individual matrix would also, each individual component rather, would have to be equal. So for instance, 1 entry and 1 entry must be the same. That gives me negative x minus y must be 0. Okay? This one also, look at the 1,3 entry. This tells me that 2x plus 2y must be 0. Okay? And what about this one? The 2,3 entry says 3x plus 3y also equals 0. And this last one gives me negative 9x minus 9y equals 0. This is a system of equations. Okay? And we know how to solve systems, right? Yeah? We can set up a representative matrix. We'll call it A pound. Yeah? So let's say we've got A pound. Here's my augmented representative matrix. And it's put my coefficients in, negative 1, 2, 2, 3, 3, negative 9. It looks a bit suspicious, but that's okay. Oh, let me not forget my solution column. 0, 0, 0, 0. Okay? And again, we solve systems by putting these things into row echelon form. Sure, you can do that. Clearly, every row after the first one is a scalar multiple of the first one. So here's my row echelon form. Okay, that seems reasonably easy. I can parameterize. Yeah. So remember, this was the x column. That was the x column. That was the y column. So let's see. I'm going to let y equal t. And so that equation reads 1x plus 1y equals 0. And so x is equal to negative t. And so everything in my kernel has to look like this, right? It's x comma y. So everything in my kernel has to look like negative t comma t for some real number t. So clearly, this is one-dimensional. My kernel is one-dimensional. Okay? Because again, all the things that look like this, I only get the one choice, right? I get to pick t. And that one sort of free choice for me, that's an indicator this is one-dimensional. So I can plug in any value for t I want other than 0 and get a vector to serve as a basis for this. I'll use 1 just because. Okay? And then I can then state, okay, the kernel of t is the span of negative 1, 1, right? That's my basis vector, right? All right. That's not all of R2, is it? No, no. And so let's think about our rank nullity theorem here, right? We know that the dimension of my domain is 2, right? So the dimension of my domain is 2. And that's got to be equal to the dimension of the range, which I don't know, plus the dimension of the kernel, which I do know, which is 1. Well, this helps me out already because I already know now that my range has to have dimension 1, right? Yeah, it's going to be a span of exactly one vector from the codomain, right? Your range lives inside your codomain. So let's see if we can't find the range, right? Well, now that I know the range is only one-dimensional, I only need one vector that looks like this to serve as a basis vector. Well, that seems pretty easy, okay? That seems pretty easy because I can just plug in a vector xy to get an example, right? So again, this information implies that the dimension of the range is 1. This means I need one basis vector, okay? And for a one-dimensional space, that's any vector except the 0 vector, right? So plug something in, right? So if you're looking for the range in this particular case, the range of t, okay? So I'll take t of 1 comma 2. Doesn't really matter what you plug in, but sure, 1 comma 2, okay? That gives me, let's see, negative 1 minus 2, that's negative 3. 0. 2 times 1 plus 2 times 2, that's 6. 0. 3 times 1 plus 3 times 2, that's 9. Negative 9 times 1 minus 9 times 2, that's negative 27. Okay? And you'll notice that this is a scalar multiple. So this is negative 3 times 1, 0, negative 2, 0, negative 3, 9. Okay? Yeah. And so this can be operated as a basis vector, right? Now, in this particular case, I just plugged in one value because I could, right? Yeah. Could I have found my range, or at least a basis vector for my range, without doing that? Well, certainly. I'm going to do this a slightly different way now. So I'm just going to write this down. So my range is the span of 1, 0, -2, 0, -3, 9. Okay, so we can do that. What if I just took a general outcome here, and what if I did a little bit of arithmetic here? So I take -x minus y, 0, 2x plus 2y. I'm just writing down the formula for a general member of my range. Yeah, just something that came out of this. And you'll notice, obviously these terms are all a little bit fishy. Let me factor out some common factors here. Okay. So this first one, that's -1 times x plus y, 0. Factor out a 2 here, I get 2 times x plus y. Yeah. Here I've got 0. Here I've got 3 times x plus y. And here I've got -9 times x plus y. Okay? And so it kind of looks like almost every one of these components here has an x plus y. And I would actually claim they all have an x plus y. Yeah? Well, how is that? Well, is there any difference between writing 0 here and instead writing 0 times x plus y? Yeah? And here, instead of writing 0, write 0 times x plus y. And so now every single one of these terms is really some multiple of x plus y. Well, let me factor that out. So this is x plus y times -1, 0, 2, 0, 3, -9. And there's my basis vector, right? Because for any vector xy, x plus y is a fixed value. Okay? And so you'll take whatever that is and you'll just multiply it times this. This here is my basis vector. Okay? So these are not overly terrible problems. I cannot give you a fixed strategy to come up with all of these. You won't do them all the same way because the spaces are very different, right? You'll find kernels and ranges in different ways just depending on what you run into. But I gave you guys a reasonable number of homework problems. I don't want to say a lot, but it's a reasonable number. And if you work through those, you should have a better grasp on how to handle these things and how to sort of approach viewing these transformations in terms of their kernels and ranges. Okay? All right. See you guys next time.